back, everybody, to the final session of CCN 2022. We are going to close out the conference with our third GAC, What is the Place of Planning? And I'm going to hand over to Espinosa, who's going to be the Master of Ceremonies.
Thank you so much. How you doing, everyone? Hello, I'm Espinosa. I work with Malcolm MacIver at Northwestern University. We're going to have a GAC. Everybody should be tired. We made it. It's the last day. This is the last event. Congratulations. And thank you so much to the organizers. It's been a wonderful conference. We're going to start with a question. What do you think planning is most useful for? And I've been told that we didn't have enough QR codes, so I added a QR code to my presentation right there. If you can go there and answer this question, and we're going to answer the same question later on, and we want to see if you change your mind over the course of the GAC workshop. Just going to give you like a full 2 minutes to do this. No more than that. I'm very strict with the time. All right, if you already answered, it's because you wanted to. So thank you so much. We're going to move on. The first thing is the schedule. We're going to try to keep things on this schedule. We're going to do our best to do that. I'm going to give you an introduction. I'm going to talk about the collaborators and the controversy a little bit, and then we're going to go to the speakers. We have one speaker that's going to be on video, and then we have a Zoom speaker. And we're going to have a group discussion before we go into a break, and then we're going to come back, a few more speakers, and then we have someone that really want to have a discussion today that's going to lead the discussion at the end. I've been very lucky. This is a wonderful team of collaborators. You probably know some of them, or most of them except me, probably. This is a fantastic team. We have Malcolm MacIver, Nathaniel Dahl, David Radish, Jane Wang, Mark Ho, Jessica Hamrick. They are all wonderful scientists, Bradley Study. And the controversy that we want to tackle with this GAC is, are there problems that are fundamentally require planning and cannot be solved via model-free learning? And it's a complicated question, so I want to address this question from kind of like my perspective, how I see this question. And for this, I'm going to need the help of a giraffe. Which is a weird animal, has this very long neck that doesn't seem to belong in nature at all, right? So we don't see many animals with long necks anymore. Maybe dinosaurs were having some of those, but not anymore. And also have weird features. It's awkward. It makes it really hard for the giraffe to walk around, to sleep. It requires like special valves to actually move the blood all the way to the brain. It doesn't seem to be very functional. However, the giraffe neck exists, right? So we know it exists. It's there. We can observe it. And then we know that it's a process of it's a result of an evolutionary process. So that means that at some point the giraffe or the ancestor of giraffe had a very short neck, and we can see it there. And eventually it was beneficial for the giraffe to have a longer and longer neck. And biologists, they kind of agree that it was because they switched from eating grass to eating the leaves on the tree, because there was less competition there. There were less animals that were eating those leaves. And the calorie intake eventually created a benefit for having longer necks. And over generations, those necks got longer and longer, and we end up with a giraffe, with a modern giraffe. And what is the point that I'm trying to make with a longer neck? Is that we know planning exists, right? So we know, we're almost certain, I think David is going to try to convince us at the end, that planning exists. But it's a very expensive process. And if we are just talking about like how to select action, it's very expensive. It involves a lot of tissue and a lot of energy. It's very slow. We know that we cannot simulate things very fast. And we have a lot of alternatives. Not a lot, but we have a few alternatives that were there before planning existed. So why planning exists? And that means like from this moment, and what you see in here is an historical moment, is the first animal that ever imagined two different futures and selected one of them. This is the picture I actually took. From this moment on, that benefit of having planning processes in the brain was persistent enough that millions of years later, we can plan on abstract objects, concepts like money or plane tickets or places. So from this primordial plan to now, that selective process kept on, still working, hopefully, and that pressure changed and shaped the way that we develop this ability. So that means if this is a constant benefit, right? So if we had constant benefit on we get constant benefit for planning. If animals get constant benefit from planning, seems to be that there is an opportunity there for be better than other methods, and that benefit, that opportunity there is persistent, and that will drive a process from less planning to more planning when we have those same circumstances. And then we turn around and we see, well, that's nice. And what happened in all these years since we started doing some planning in algorithmically in AI or machine learning? And what we see is like history kind of repeated. Right? So we started with very basic planning in 1951. This was a checkers game. It played very bad checkers, but it played checkers. It was something, right? So people was able to play against the machine. This was the first time that it happened. And people was fascinated with this. And also looked like we can solve some of these problems using kind of like planning a strategy would make sense at that point. And people was in love with this solution, apparently because we kept doing just planning for a long time. In 1997, everybody talks about AlphaGo and AlphaZero and all those things. So they're fantastic, don't get me wrong. But in 1997, just doing planning, right? Look-aheads, Alpha, Beta, look-aheads. Deep Blue defeated the world champion of chess, that was Kasparov at the time. And it was just planning. There was no neural networks, DQNs, deep learning, all those things. They existed in theory, but then not in application. So at this point, we have a planning algorithm that had superhuman abilities for a specific task. And then we kept going. So planning was still the king. We had POM-CP in 2010. And it was fantastic. Now we can do POM-DPs, large POM-DP solutions. So partially observable scenarios, we can still tackle those with planning. And then this is where planning started losing its sexiness. In 2013, a DQN show up. And this is revolutionary. Now we can tackle problems that usually we will attack with planning using a learning algorithm. And this is completely model-free. And now this is real time, and it's complete, and it's partially observable. So there are a lot of things that we thought it was, this is a planning domain. It's no longer. And this kept going. Well, AlphaGo does planning and learning, so those two things seem to be getting together. And then, well, this is probably the AI event of the decade. So this is always superhuman. So I will say that AlphaGo is superhuman. And then we have, in 2019, something that was, for me personally, it's a landmark because I played StarCraft for a long time. This is an extremely complicated game with hundreds of units that need to be controlled in real time. Like it is, and you have partial observability, you have up to 4 different adversaries. It's very complicated, and this was solved completely model-free. So at this point, I would say that year, I think I had a meeting with Malcolm. It's like that was the lowest, the lowest place year for planning. I remember we cried a little bit together. There was like, oh, planning's dead. But then Mu0 came around, and Mu0, I think it's a state of the art. And I haven't heard anything better or newer that it's better than Mu0 for reinforcement learning. And it does very well, and it uses planning in different ways. And Jessica Hamrick from DeepMind is going to talk in a minute about how that works. And I just wanted to add, this was a last-minute thing that we wanted to add. This is a very new paper, a very fresh paper. This is completely model-free, and it's a game that's called, an agent and play, a game called Stratego. I just added this, so I apologize. And the thing, why I wanted to add this, I played this game in the 90s. I'm very old. And then the idea of this is why this is very important, because to win in this game, you need what we consider human behaviors. You need deception, you need bluffing. You cannot win if you don't use those. And also you need to create a model, theoretically, you need to create a model of what the response of your opponent. If it's more of a liar, it's more of like, it's telling the truth, what kind of player am I playing with? Because it's a very complicated human strategy game, and almost diplomacy. So, and this was solved completely model-free. So that's the part that was kind of like confusing to us. But anyway, this is the last minute ad, so I'm not gonna go into details there. So we're gonna go back to the controversy. Like, wait, it doesn't look like planning is getting more and more complex, that we're adding more layers to planning. It looks like we are some kind of like moving away from that trajectory, and we are combining planning with model-free, or even sometimes just not using planning at all. So what's going on there? So are there problems, and this is the topic that we're going to visit, are there problems that fundamentally require planning? That domain exists in the problem phase and cannot be solved via model-free learning. And, oh, sorry, what did I do? I think, well, and the next speaker, the person that is going to clarify a little bit, especially on the mu0 topic, is Jessica Hamrick. She works in DeepMind, and she's a senior researcher there. And the last paper she published is fantastic. If you haven't read it, read it, just take your time and do it in your way back home. She has a PhD in psychology from UC Berkeley, and she couldn't be here, but she's going to explain why. If this works. Yes.
Hi, my name is Jessica Hamrick, and I'm a research scientist at DeepMind studying model-based reinforcement learning. I'm sorry I'm not able to be at the workshop in person or even remotely. I'm in London, and I have a new baby who's demanding my attention in the evening and at night. So with the difference in time zones, it just didn't quite work out. But hopefully this recorded talk will still spark some interesting discussion, and I'd be happy to follow up with any questions over email. A prominent idea in cognitive science and neuroscience, and the focus of this workshop in GAC, is that the human mind is, at least in part, so powerful and flexible because it builds rich internal models of the world and uses them for planning. Recent years in machine learning have seen an explosion of work that, similarly, builds models of the world and plans with them, with the citations I'm showing here representing only a small slice of the literature up to 2019. These systems are often referred to under the term model-based reinforcement learning, and they've achieved some impressive results. For example, planning is a key component in systems that can beat human grandmasters at Go, solve a Rubik's Cube with a robotic hand, design molecules, and pick up objects in a cluttered scene. Moreover, planning-based systems perform as well as model-free systems at a variety of tasks, though often with better data efficiency, including playing Atari games at superhuman level, controlling the movement of simulated avatars, solving difficult puzzle games like Sokoban, and navigating through a 3D maze. These methods are often motivated explicitly by model-based reasoning and human cognition, or at least by human-level capacities for generalization and transfer. For example, an ability for precise and sophisticated look-ahead, being able to manipulate previously unseen objects, or better generalization across states. But do these methods actually exhibit generalization to the extent that we see it in humans? And to what extent is it that the model-based part itself that supports such behaviors? In recent work that I've been doing at DeepMind, we aim to disentangle the role of planning in model-based RL. We've been focusing our analyses on mu0, a recent model-based system that achieves state-of-the-art performance on various domains from Go to Atari. And by state-of-the-art, I mean that mu0 can far surpass human performance in all of these domains, as well as other machine learning approaches. It's worth pointing out that mu0 incorporates many of the same components as other model-based systems, so by studying how mu0 works, we can draw conclusions about other model-based agents as well. So let me start by giving you a quick overview of how mu0 works. First, the agent gets an observation from the world. This might be, for example, an image of the game that it's playing. Then it uses its model of the world to plan what the best action is to take from the current scenario. The particular form of planning that mu0 uses is what's known as Monte Carlo tree search, or MCTS. At a high level, MCTS works by the agent imagining future possible states it could be in, and then which actions might be good to take from that state. Importantly, it also uses a learned distribution over actions, known as a policy, to help guide the search for the best action, as well as what's known as a value function, which estimates how good each imagined state is to be in. You can think of the policy as an educated guess. The agent imagines the best action that the policy recommends, and then estimates how good the action actually is with the value function. It then tries the second best, and so on. So after planning, the agent chooses the best action it came up with and executes it in the world. This might be something like move the joystick up. Then it also uses the results of planning to further improve the policy and value function. You can think of this as like a bootstrapping procedure. The search improves on the policy and value function, and then it uses the improved policy and value function to update its neural network. So to be able to draw generalizable conclusions about the role of planning in model-based RL, we tested mu0 across a wide range of tasks that varied in their branching factor, time horizon, and sparsity of rewards, and variability of initial conditions. And in particular, we have 3 continuous control tasks, Acrobat, Cheetah, and Humanoid, 2 Atari games, Hero and Ms. Pac-Man, 1 procedural Atari-like game called Mini Pac-Man, a puzzle game called Sokoban, and 9x9 Go. First, we looked at different ways of utilizing the search in mu0 and how much each use of search contributed to the overall performance of the agent. Starting off, a model-free agent that doesn't use planning at all only achieves about 50% of the full performance of mu0, indicating that using planning in some capacity does indeed provide benefits. We can look at the other ways of using planning, for example, just to provide a learning signal for learning the policy, but only acting reactively using the policy, so not using planning to select the actions. This gives us a substantial improvement to about 68% of full performance. Similarly, using planning just to select the actions during training, which you can also think of as basically selecting the data distribution to learn from, but where the learning itself is done via a model-free method, this also gives a similar improvement to about 67% of full performance. Combining both ways of using search, both for learning and for acting, reveals that they're complementary, and that doing so explains the majority of mu0's performance, about 90%. Finally, we can incorporate search at test time too, but we find that it helps very little in most domains, except for Acrobat and 9x9 Go. So overall, we find that the primary contribution of planning is to construct better learning targets and data, rather than acting at test time. Why does search at test time seem to be not that useful? To investigate this result further, we took a trained mu0 agent and just modified how much search we had it do at test time. In this plot, the y-axis compares performance to that obtained by the default mu0 agent, with values greater than 1 indicating improved performance and values less than 1 indicating decreased performance. What we find is that increasing the number of simulations beyond the 50 simulations used by the default mu0 doesn't help performance, and in fact may hurt it. One hypothesis might be that the learned model is imperfect, and thus deeper planning leads to more accumulated error. To test this, we redid the experiment, but with a perfect model. We find that the results largely hold, though. Even with a perfect model, we see only small benefits of more planning at test time. But how could this be if we have a perfect model? How could using a perfect model of the world not improve performance? We hypothesized that other learned components besides the model, in particular the policy or the value function, could be affecting their performance. So to test this, we used a different form of planning that just tries every action exactly once, scores it with the value function, and then picks the best one. What we found is that using this strategy, any amount of planning hurts performance. This is because the value function gives bad predictions for some actions, and in particular, those not seen during training. This is what explains the lack of improvement we see from planning, even with a perfect model. The errors in the value function prevents the planner from actually finding better solutions. And this is important because it means that the model is not the only thing that we have to care about. We have to care about the policy and the value function as well. Finally, we explicitly tested how well mu0 can generalize to new environments and whether planning might help here. To do this, we trained mu0 on a finite collection of randomly generated mini Pac-Man levels and tested the resulting architecture on a handcrafted test level that you can see here. With a learned model, increasing planning only weakly improves performance and eventually degrades it. With a perfect model, planning helps more, especially with fewer training scenes, but again, too much planning can hurt and still does not achieve perfect generalization even after thousands of simulations. So again, this means that even with a perfect model, it doesn't guarantee good generalization performance. Okay, so to synthesize all the results I've just presented, I think there are two main things we can take away. First, planning seems to be most useful during learning and less so when making a decision at test time or in the moment. As we found in most environments, planning at test time, in the moment, added very little, even if using a perfect model, but it made a huge contribution when used to generate a learning signal or data to learn from. This is not to say that planning is never useful when acting. After all, we found it made a huge difference in two domains, Go and Acrobat. But this result has made me wonder whether the set of domains in which planning is useful at test time is actually perhaps more narrow than is widely believed. The second takeaway is that if we do want to use planning at test time, we need to have good representations for multiple components, the policy, value function, and the model. It's not sufficient to just have a good model of the world. In any sufficiently complex environment, we need some way of guiding the search towards better solutions, which is exactly what the policy and value function do. These policies and value functions need to be reliable and need to generalize just as much as the model, or we won't be able to rely on planning to make better decisions. And just to emphasize this point, I want to briefly summarize some work we've been doing, some follow-up work we've been doing, led by Ankesh Anand and Jacob Walker. In this work, we trained mu0 on the ProcGen benchmark, which is a suite of procedurally generated games that involves training on a smaller set of levels and then needing to generalize to a larger set. In addition to training regular mu0, we also implemented a version of mu0 that incorporates a more sophisticated method of representation learning for its policy, value function, and model. I'm not going to get into how this representation learning works. If you're interested, you can check out the paper for details. But what's important is just knowing that we found a way to improve the quality of mu0's model, value function, and policy. Our results show that this improved representation learning makes a massive difference in generalization performance. In the figure on the right, the y-axis shows the generalization performance on the test set, and the x-axis shows how long the agent was trained for. You can see that the red curve, which shows mu0 with improved representation learning, generalizes way better than mu0 alone, which is the black curve, or a model for agent that doesn't use planning at all, which is the yellow curve. And with this form of representation learning, mu0 not only generalizes better at the end of training, but it's much faster to learn too. So I think this result really drives home the point that effective planning, especially for generalization, requires having good representations for multiple components: policies, value functions, and the model. But these results also pose a bit of a conundrum. What if we can learn good enough value functions and policies, do we even need planning at all? I would definitely say that we still need planning during training. All the results I've showed you today constitute strong evidence that using a model of the world is really helpful for learning. But I think the evidence that it's helpful at test time to make a decision in the moment is more mixed, at least when it comes to the way we train modern deep learning agents. It clearly helps in some situations like Go, but perhaps not in many others. As a cognitive scientist, I believe deep down in my heart that this isn't true and that planning really ought to be useful at test time. But at least what we're seeing from the machine learning side, it does sort of question this assumption. But I'm hopeful that perhaps this collaboration might help us shed some light on this issue. Okay, so just to wrap up, I want to thank all of my co-authors, and you can find the full citations for the two papers I talked about here. Thank you very much for your attention, and I'm excited to seeing how this generative adversarial collaboration plays out. Thank you.
She's not there, but all right, let's move on. And that's it. And we don't have we cannot have Q&A for Jessica, but if you contact us with any questions after the GAC for any question that is for her, we will definitely forward this. And now we have our following speaker, Jane Wang. She's also a researcher for DeepMind. She has a PhD in applied physics from the University of Michigan. She's also a wonderful scientist, and she's here via Zoom. We're going to have her talk, and then we're going to have 5 minutes for Q&A after. There you go. Jane, can you hear us?
Yeah, the host has disabled screen sharing.
Oh, can you? That's very important. Can you try now? Excellent. Thank you.
Great. All right, first of all, I want to thank the Herman and the other organizers for inviting me to speak today. And I'm really looking forward to having this discussion after my talk and seeing all the other talks. This is a really interesting topic because, you know, in the course of my career so far in AI, I haven't, you know, thought very hard about planning. I have been mostly thinking about just deep RL agents and how they can do you know, various different kinds of tasks. But in really reflecting a lot about what I have learned and have observed about agents, you know, I thought that it's actually pretty interesting the things that the relationships between their capabilities that I've observed and planning. So. So just to get on the same page, for me, you know, well, one possible way of defining planning is to think of it as model-based decision-making. So, for instance, you have an internal model of the world, and we're therefore able to use that model to inform selecting what actions to take to achieve our goals. And planning in deep RL agents takes the form of for instance, Monte Carlo tree search, or you know, more like prominently, as we've seen recently, and as Jessica was speaking about, we have AlphaGo, AlphaZero, and MuZero, which are able to solve either, you know, two-person games or even Atari single-person games. But what I want to emphasize in this talk is that even model-free deep RL methods, the ones that don't have this kind of explicit search process that is within AlphaGo, Zero, for instance. Even these model-free methods can yield what is apparently model-based behavior if the task requires it. So, so yeah, I'm trying to aim to first answer, can deep RL agents display behavior that looks apparently model-based? To answer that, you know, I'm actually going to go back to a fairly old paper at this point that I worked on in 2018, where we looked at a quintessentially model-based RL task. And to Nathaniel, this should be very familiar because he introduced it. This is the two-step task. This was actually my first experience with model-based RL. When I was learning about it, this was kind of the task that I learned about. So I'm giving a simplified version of it here in case you haven't seen it before. So essentially what the player or the agent does is they start off in one state, the same state every time, and then they choose between action 1 and action 2. And then that allows them to transition to one or two subsequent states where there's a probability of transitioning to either of them. There's a more common transition. For instance, action 1 will transition you to this left state. And then an uncommon transition, for instance, action 1 will transition you into this right state. And then following that, you get a reward following some probability that that can vary over time. So model-free and model-based strategies will predict different choices based on the outcome of what happened on the previous trial, and that's why this makes it a really good assay for model-based behavior. So, for instance, model-free strategy will predict that if you were to observe a common transition and you were rewarded, then you should make the same action the next time, right? Because it's model-free. You don't have a notion of state transition probabilities. Model-based, on the other hand, has this notion of rare versus common transitions, and so if after observing a rare transition, you actually got rewarded, then you actually would be less likely to make that same action on the next trial. So this was a really nice task because you can also do it in humans and in animals. And this data here is taken in particular from Kevin Miller and others. In 2017, they tested it with rats and found a pretty model-based signature of behavior. And we see similar kinds of behavior in humans. It's kind of more mixed in humans, but we really nicely see that at least it's not completely model-free. And if we were to train a deep RL agent, which we call a meta RL agent, on the same task, we find that it also displays a pretty clearly model-based pattern of behavior. And this is after we have frozen the weights of this agent. So this is all sort of just happening in its internal hidden state, its internal dynamics or memory. And this struck us as quite remarkable because this meta RL agent is, again, trained via model-free reinforcement learning. So, and yet we see this automatic emergence of what amounts to model-based behavior, which we didn't build in. So we didn't have this explicit search or any kind of explicit model that we've incorporated into our agents. Okay, and this brings me to a wider theme that I want to really emphasize in this talk, which is the power of structured sequence learning. So what does that mean? Well, a large part of my previous work has looked at deep RL agents, and in particular these, meta RL agents, which have memory in them, and they sort of maintain as hidden states, and they're trained on a distribution of tasks, and by training them in this way via memory-based meta learning, they're able to absorb structure present in the distribution of tasks. And so this will actually allow them to necessarily be able to represent that task structure. And they do this because of two facts. So this meta RL agent is trained given a sequence of observations, given observations from a sequence generator with structure. So they're not given just sort of arbitrary observations that doesn't have any internal consistency. But it's in fact a generator that has structure. So it's think of it as like the internal game engine. And this allows the meta learner to predict future observations from past history. And because the memory of a meta learner is inherently limited, we only have a finite number of parameters that we can have in our LSTM, for instance. This actually forces it to have a representation of that task structure contained within it. And if you train it for long enough and it's successful, we have a resulting meta learner that learns a state representation of sufficient statistics that efficiently captures task structure. So so to kind of more better to illustrate this idea, this was taken from paper led by Pedro Ortega, which is a really nice example. And it's extremely simple, like thought experiment of let's just try to learn, get an agent to predict the probability of a coin landing heads or tails up, right? So it's got an unknown load of probability of landing heads up. And so we're just going to make a bunch of observations, and we're going to try and see if we can learn a prediction based on these observations. And so what is illustrated here is essentially a minimal finite state machine for a predictor of coin tosses with a fixed known bias. The dark and the light state transitions here correspond to observing the outcomes of head and tail respectively. And the states are denoted with number of heads and number of tails. So essentially you can see that as we are making different observations about how many heads and how many tails we've seen, it doesn't so much matter what we like the specific sequence of things that we've seen. The minimal state representation only cares about the total number of heads versus tails that we've seen, right? So I can take different paths and I'll end up in the same state. So that's what this means by a minimal state representation. If we were to train just a LCM, just a neural network with memory to do the same task, and then we just visualize its activation dynamics, so just using like PCA or something, we can actually see something really nicely structured in its internal sort of state space that is that looks very similar to the canonical or like the ground truth representation of what's happening in this task. So so this leads me to my next question, which is, do agents actually need explicit planning? So as Jess showed wonderfully in her talk, it seems more important for at least agents that are doing DRL tasks to have correct representations for the policy and other agent components. And that's what allows explicit planning to be useful. And I've also observed this in testing out different model-free DRL agents on an environment that we recently released called Alchemy. And Alchemy is a game in which you're trying to essentially transform different stones into what we call these highly valued gold stones, which gives you the most amount of reward. So those are the stones that you're trying to get, but you're trying to transform them by dipping them into these different kinds of potions. From episode to episode, some elements of the game sort of remain consistent, while others will change from episode to episode. So you have to kind of like rediscover the rules, like what do all the different potions do, and which stone is the best stone right now. So and we do have this notion of different episodes and different trials within an episode. So you have to do different kinds of experimentation because there's a really like deep latent structure within this task that you have to discover over the course of playing within an episode. So we call this the chemistry, which you can kind of see examples of here on the bottom right. And I won't get into the details of what's really represented here, but the main point is that in order to discover what are the underlying chemistries and how to get at the gold stone, you need to do different kinds of experiments and to be able to test out these hypotheses. Okay, I said before that the structure is latent, and what that means is essentially that of course they're not directly observable by the agent, and because the agent can only see the physical properties of the stone, but the physical properties of the stone, such as the size, color, and shape, are only related in a hidden way to the to sort of like the internal coordinate system that determines the value of the stones themselves, and also determines how the potions affect them. So, so again, it's only through experimentation and inference that people are really able to learn the underlying rules of stone transformation in any given episode, and then to plan and execute the appropriate sequence of transformations to obtain the highest value stones. So this is a pretty difficult task. So if you can imagine, you have to do planning in latent space. And we have two different versions of it. So we actually have a fully 3D version, which looks like this, where you have to manipulate the stone around to the different potions and dip them and then put them into the cauldron. We also have a more symbolic version where each action can just immediately transform or apply a potion to a stone. And you don't, and you're given the observations in symbolic format. In our paper, we essentially, analyzed two pretty powerful DeepRL agents. And the results here are shown for BMPO agents on both the 3D and the symbolic task. And we compared to different what we call reference agents, which are essentially just benchmarks that tell you how good the performance is. So the dotted line here is how you would perform if you just sort of randomly dipped stones into the different potions until you got a better stone and then you dropped it in. So it requires no planning whatsoever. Oracle is if you knew the ground truth of the chemistry, you didn't have to do any experimentation. And the ideal observer is how you would act if you were sort of doing optimal exploration and exploitation, right, over the course of a trial. And you can see that, just completely, naive, like model-free agents, they're not at zero. They can, get some score, but they're essentially sort of acting quite randomly on this task. So in the paper, we tried various methods of providing different kinds of privileged information to the agent or different auxiliary tasks to encourage different kinds of internal representations. There are a lot of results I can't really get into. I just basically want to highlight these particular results, where the bars on the left here are the same results that I just showed on the previous slide, and the ones on the right are if you have an auxiliary task, which is essentially like a prediction task, which is designed to give rise to the right useful representations for alchemy for our agents. So essentially, we're trying to almost like handhold the agents to get the right representations within its internal states, and then use RL to sort of do better on the task. And you see that it has a huge benefit, especially in the symbolic version. So the overall, upshot of this is that we found that otherwise highly performant DeepRL agents, such as the ones we tested here, and these are agents that can solve a host of other tasks, Atari, Labyrinth, it's like 3D rich tasks. They're not able to solve the challenge that alchemy poses, which involves planning in this like latent state. So essentially performing inference from observations is quite difficult. However, if the structure or these correct representations were instead provided, or they were sort of nudged to learn those representations for themselves, so that essentially they were no longer latent, the agents could indeed make use of this information and essentially do what appears to be planning when given the proper representations, because you do need to do planning in alchemy in order to be able to perform at this level. And so essentially, I think these results are pretty consistent with what Jess found as well, which is that the limiting factor in these DeepRL agents isn't the planning itself, but really learning the proper representations on which to do this planning. And so if you have other methods of inducing those, then during evaluation, you actually are able to perform much better. Okay, so but this kind of implies that we have this bottleneck on learning these good representations. So and this brings me to the last part of my talk, which is thinking about, well, actually, we have seen that there is a good method of getting structured representations, and that's just using the huge data at scale. So this is going to be me talking about I'm sure all of you have seen these models that have been dubbed I guess like foundation models, because they are essentially sequence learning models. So they're doing sort of like self-supervised prediction of next tokens. but they're just doing it at a huge amount of scale. They're doing it on all of the internet's data, or on Wikipedia, or on entire captioning model, or captioning data sets like Photostock and so forth. So the two biggest examples are like language models such as GPT-3, or also Gopher from DeepMind, and DALL-E, which you might have seen, where you can actually predict, or you can generate images from just language descriptions, so completely new images that have never been seen before. And we even have multimodal vision language models like Flamingo, where you can actually have a conversation with them based on images, right? So in this particular example, you can instruct Flamingo to essentially do the Stroop task, where you can tell it to do look at a particular image, and then to say, in this case, say the color that the image word is written in. And so it's, I think it's hard to argue at this point that there isn't some like really interesting representations and structured representations that's being learned by these models. And, just in like the general kind of atmosphere of AI and in the field at large, I think people have started to see different signs of this. Such as that, I mean, it's not entirely clear that this is reproducible, but I saw this interesting tweet that talks about like, well, maybe DALL-E has a secret language because it tends to generate like this gibberish language, but then if you were to feed the language back in and ask it to generate something, it seems to generate consistent things, meaning that it's sort of developed its own name for certain concepts. And I think this is a really interesting, like maybe incipient new field of applying, cognitive psychology style methods to looking at these large scale models. And a really great example of work in this vein is came out of DeepMind, led by Stephanie Chan, in looking at data distributional properties that drive emergent in context learning in transformers. So I don't have time to really get into it here, but if you're interested to try and understand better these large scale models, I recommend you give it a read. It really systematically kind of tries to understand what are the different properties of the data and how we train these models that allows them to do like few shot in context learning. Okay, and but what about decision making? So I just want to kind of like bring it full circle back to what we talked about in the beginning, the two-step task, because this is really interesting paper that recently came out from Marcel Binz and Eric Schultz, which actually just applied a plethora of cognitive psychology tasks to GPT-3. So they sort of turned all of these tasks into text. So the two-step task has been texified as on the right here. You can see, you can kind of like briefly scan that. And then if you feed it into GPT-3, you ask it, well, what do you want to do? Interestingly enough, it appears to display, model-based signatures similar to how humans display. Now, of course, this comes with the caveat that it's, these large language models tend to be kind of susceptible to adversarial attacks, or they tend to be very unpredictable. So maybe you need to sample multiple times to kind of to see interesting behavior. But I still nevertheless think that this is really promising, given that they were never even trained to do any of this. So just to conclude with some final thoughts and caveats or questions, I'd say that overall, my sense and my I guess answer to the initial question posed is that the amount and distribution of training data and tasks are critical for the performance of the resulting deep RL model. And explicit planning doesn't seem that critical for many of the RL tasks that have been presented to agents, at least with the exception of things like Go or tasks that require really like in-depth search, where you like literally cannot have seen every single possible iteration. And good representation learning via, for instance, self-supervision, as is done in large language models, seems to naturally lead to learning at least somewhat useful models, and thus can give the appearance of planning in a lot of circumstances. So this is, of course, with the caveats, because they are very sensitive to how they are prompted, and they don't show a robust ability to plan, especially when required to do long chains of reasoning. So I guess I want to end with a question that I want to pose to my fellow GAC organizers, which is planning really a discrete quantity, where it's just an all or nothing thing, or is it something that exists on a spectrum where it can be, it ranges from being more model-free and very implicit to all the way to being, autobiographical. I can sort of imagine myself planning to do something, and it is like a very explicit process. So, so with that, I want to thank everybody for your attention, and I'll take questions.
Thank you so much, Jane. We have some time for questions. If you have any questions, you can use the microphones. What? Is that working?
Jane, can you hear me?
Yes.
Okay. So this is Dave Reddish. You can't see me, I know, because it's all behind. It seems like all of the tasks you're looking at exist in stable worlds. And it sounds to me, if I've heard you correctly, that what's really going on is if the agent has enough time to find the stability within the world, which can be incredibly complex, then it doesn't need planning. Is that a fair assessment?
Well, it depends on what you mean by stable, because when we consider, meta learning, in order to do meta learning, you need a distribution of tasks. So you are changing it every episode, and in a lot of situations, like a lot of times you can actually train an agent to have unsignaled like episode transitions, even where sort of things are changing without it being like reset. And so I think that, but like that said, you need the distribution from which you're sampling these tasks to be stationary. So you're right that you can't completely start to do a totally different, set of, like you've reversed all of your reward contingencies and then expect the agent to be able to handle that.
Thank you very much. I have a question about a statement you made about the meta learner as opposed to planning. My question is about meta learner. At some point you mentioned that the meta learner eventually learns a state representation of sufficient statistic. So I wonder, number one, is that from the intuitive point of view, that makes sense. However, theoretically speaking, this is a huge leap for this to happen, because essentially that means everything the statistics literature has been doing from 20s to about 60. So that 40 years would be within this, which is wonderful if that happens. And the other thing is that if that is happening, is it the actual sufficiency which matters or the minimal sufficiency? Because these agents have, as you mentioned, have limited capacity. So somehow all the ancillary information has to be squeezed out so that you're left with minimal sufficiency. So is there any proof that these would converge to a state of minimal sufficiency as opposed to sufficiency?
Yeah, okay, so you have definitely caught me on my, I was trying to be really glib on that particular point. So I think Pedro explains this much better in the paper, but yeah, you're right that we cannot guarantee that it converges to minimal sufficient statistics, because you can never be sure that you have that you have like a bottleneck the amount of like you can always have learned, redundant states for like for the same sort of minimal sufficiency state. But that said, so this is generally true if you consider training a meta learner on enough data, right? So in the like asymptote of having seen every possible task from your task distribution, then you expect that you would be able to essentially recapitulate the generator that has been generating those tasks. And given limited enough memory, then you would expect that it would at least look somewhat like it would look somewhat like the actual generator of the task if you were to plot it in state space. That said, I've looked at a lot of these agents that have been trained to do different tasks, and it's not always completely clear that you have captured, you often see redundant states, for instance, or sequences where the state seems to jump from one to another part of the state space for no apparent reason. And so I do think that in practice, it probably doesn't happen very often that you get like minimal sufficient representation.
So the statement is also from a practical point of view rather than a theoretical point of view. Is that fair to say?
I'm sorry?
So the statement itself is more of a practical point of view rather than a theoretical point of view. Is that fair to say?
Yeah,
Okay.
I would say, nothing is like proven theoretically.
Okay, thank you.
Thank you so much, Jane. There's another question right there. Sorry, my bad.
No problem. So just sort of partially prompted off of what David said on the stage. All of these tasks are kind of viewed as single agent interacting. Even the first speaker, their image was of a dinosaur imagining a bee, which is another agent. So I'm wondering, in this theme of, well, maybe you need modeling to decide what it is you should go after and what it is you should learn, how would an environment with multiple different agents acting affect whether you need planning to decide what to learn versus simply learning a structure and acting model-free?
That is a great point, and I've dabbled a little bit with multi-agent DeepRL, and my sense is that it always, at least with like these model-free agents, you wind up not getting super stable performance. So a lot of times you see performance sort of rise and then it collapses down again. I think that's because of this point that you're hitting on, which is that they don't have this explicit notion of like a modeling another agent in my environment, which can also change, right? So if you just have model-free learning, then trying to model a stable structure in your environment, even one that is that might like transition from state to state, but in a predictable way, that's going to be a lot easier than trying to model some quantity that is going to impact your environment in an unpredictable way, but that is its own agent, right? And could possibly learn from your own actions. And so that might require an entirely different module that maybe is why humans, we feel like we can do such explicit planning.
Thank you.
Any more questions? All right. Thank you, Jane.
Thank you.
All right, I'm gonna pull my second QR code. The idea is, we're gonna ask you the same question, but now we want you to get in groups of 5 if it's possible. And the idea is, try to discuss a little bit, see if your answer remains the same after having these 2 talks. And we're gonna have, I'm gonna probably give you 10 minutes, 12 minutes to do this task, and then we're gonna have our break.